We are going to be talking about centripetal acceleration. In order to talk about centripetal acceleration, we need to just do a little bit of review and go back to centripetal force. It is the force that is required to keep an object in circular motion, and we have used this equation already in the past, and so this should look familiar. So remember that the centripetal force, denoted by the big F sub c, equals mass times velocity squared all over r. And this equation comes from force equals mass times acceleration, where the acceleration here is v squared over the radius to denote that we are going in a circular motion. Remember that force is measured in newtons, which is a kilogram meters per second squared. We mentioned centripetal acceleration is center seeking, and in that it points to the center. As the object moves about the circular pattern, so in this circular motion, the velocity changes. Therefore, we are always having acceleration. If you find the resultant of the velocities, so here we have v1 and then we have v2, if you find the resultant, you will actually find the change in velocity, and what you'll notice is that the change in velocity is center seeking, and this is the acceleration, which is also pointed towards the center. Centripetal acceleration is center seeking. It points to the center. It is how quickly an object's velocity is changing in a circular motion. So remember that velocity is pretty much, it can change either by changing directions, or it could be increasing or decreasing. So acceleration is whenever velocity changes, either directions or in the speed. And here we already have a for acceleration equals v squared over r, which we got from F equals ma. Remember that velocity is measured in meters per second, and when you square this, this will become meters squared per second squared. Radius, the letter r, will be in meters. Acceleration is measured after everything is cross-canceled. It will be meters per second, which is where we get the meters per second squared. Circular motion can be horizontal. For example, a car is turning on a level surface. When you're looking at the free body diagram over here, what you'll notice is that the forces acting on the car are its weight, which is mg, and that is pulling down. We have the normal force, which is denoted as N. However, we also denote that as the capital letter R, and that is due to the road pushing up on the car. Both of these forces act vertically and have no horizontal component. The friction is pointed inward towards the center. The friction between the tires and the road causes an unbalanced force, and this centripetal acceleration is also towards the center. The friction provides the centripetal force that keeps the car turning. If that frictional force was not there, the car would just slide off and not be able to turn. Here is an example where you will need to do some calculations. Feel free to go ahead and stop this, just get the first part, and then try to solve this on your own before continuing. A 900 kilogram car moves at 10 meters per second and takes a turn around a corner in a circle, radius of 25 meters. Determine the acceleration and the net force acting upon the car. So we know that the acceleration equals v squared over r. First step that you want to do is just to list the variables and the information that you have and that you know. Here we have mass equals 900 kilograms. We have the velocity at being 10 meters per second. The radius is 25 meters. We do not know the acceleration, and we do not know the net force, but we should be able to find both. Step 2 is to solve for acceleration, and over on the left, you don't have to worry about writing this. I just wanted to have it here so that we could see what numbers I was plugging into the equation. So we know that acceleration equals velocity squared over radius. So when we plug everything in, we get 10.0 meters per second, all squared, over 25.0 meters. When we multiply and we divide and everything crosses out, we are left with 4.0 meters per second squared. Then all we need to do is step 3, solve for the net force. And we are using force equals mass times acceleration. We plug our mass in, and we plug in our acceleration, and we get an answer of 3,600 newtons. Here's an example for you to try. A 100-kilogram moving car is turning around a circle radius of 20 meters. Determine the speed of the car. Go ahead and try to solve this problem and then start the video back up. Step 1 is to draw a free body diagram, and remember to label this with both words and symbols. When you're drawing this, what you'll notice is that you have the normal resistive force, denoted as R. We have the force of gravity, or weight. And we have the friction force that is either in whichever direction you decided you wanted to make your car turn. For me, I went that my car was turning left. And I also placed that the acceleration is also to the left. I pushed it away from the force of friction just so that you can actually see it and it's not overlapped, but the acceleration and the friction force are in the same direction. Step 2 is to find the net force. Then you can substitute using the centripetal acceleration equation, solve for V, and you would have your answer. The variables that we have are listed over here on the left, and we are actually trying to find the speed. Using the equation F equals ma, and knowing that acceleration equals v squared over r, we just plug in this v squared over r into our F equals ma equation, and when we plug in our values, we solve for v, and we get an answer of 10 meters per second. Okay, so we are finished with our notes. Other than that, have a great day. Thanks for watching.